All right, let's take a look at a new technique, which is the 2 pointer iteration technique. And to help demonstrate this, I'm going to show you a particular problem, which is fairly common as like an algorithm type problem. It's the problem of palindromes. So our goal is to, given an input of a string of characters, determine if the string is a palindrome or not. And you may or may not be familiar with the idea of a palindrome. Basically, a palindrome is a string that reads the same forwards and backwards. So for instance, race car is the same read forwards as it is backwards. However, something like hello is not a palindrome because it's different forwards and backwards. You could see forwards it's hello and backwards it's something weird, right? So that would be the idea of a palindrome. It reads the same forwards and backwards. Now, oftentimes with palindromes, we also say like we're going to remove things like spaces and the non-alphanumeric characters because we don't want to include those. We just want to consider the alpha characters, so like the alphabet related characters that we have. Now, similarly to that, we're going to make sure that everything is lowercase. We don't care if it's a capital R versus a lowercase r or something like that. So we'll remove the uppercase and lowercase. We'll make everything just lowercase, and then we'll remove all of the non-alpha characters in order to get us to just a string of characters. Then we're going to check to see if it's the same forwards and backwards. Let me show you one approach to doing this, which I would call sort of the brute force approach. It's the one where we just iterate the actual string itself. In this kind of iteration technique, one of the ideas that we could have is we could say, well, what if we were to reverse the string and we were to just compare the forwards and backwards of the string, right? That would be a simple way of doing this. So let's go ahead and give that a try, and let's take a look at the approach. So first things first is that I want to define a variable to keep track of the reverse of the string, and I'm going to keep track of my current string with all of the non-alphanumeric characters removed from it. I'm going to have a variable called palindrome, which is going to track if it's a palindrome or not, which will initialize to true. We'll set an I equal to 0 and a j equal to -1, since we're going to iterate backwards through the array as well. So let's give this a try. While I is less than the length of s, we'll start with, right? What we want to do is we want to build the reversed string. So we're going to say if the value at j, so the negative index, the value at the end of the string, is an alphanumeric character, then we're going to place it onto the reverse string. So we're going to add on s at j dot to or dot lower, right? So we're going to add the lowercase of that character, right? And then similarly, if s at I is an alphanumeric value, well, then we're going to add that to our forward string. So basically, by the end of this, what we'll end up with is the normal string that we had with all of the non-alphanumeric characters removed in lowercase going forwards, and then we'll have it going backwards as well. In order to do this, we basically are going to add 1 to I on each iteration, and then we're going to subtract 1 from j on each iteration. That way j is moving backwards through the array, and I is moving forwards through the array itself. Now, one question you may have is accessing at a negative index. What's the time complexity of that? Generally O1 as well. So that's generally going to be constant time as well. So this first iteration here, this main while loop, iterates through our whole array. Everything's constant time in it, so it is going to be ON, right? This is alpha num, is also constant time. Basically what it does is it just compares the character's ASCII code to a particular range to see if it's alphanumeric. So that's something that can be done generally with constant time-based operations. It doesn't vary based on the size of the input itself. So that's the first iteration. That gets us the string backwards as well as the string forwards in lowercase without any sort of special characters. Then we're going to reset I to 0. We're going to iterate one more time. We're going to say, well, I is less than the length of that in parse, which is the parsed version of our input. And the thing is a palindrome. And then we're going to say if the in parse at I does not equal to the reverse at I, well, then palindrome is false. And then on each iteration, we just increment I to move forward in the array, right? And then all we have to do here is we just have to return palindrome, and we are done. Let's give this a try with some simple examples. So, something that may be a palindrome would be, race car, for example. That's usually a good example of a palindrome. So let's go ahead and try running that. You'll see that we get true. Another example of a palindrome would be mom. That's a palindrome, same forwards and backwards. So that one seems to work. But if I put in something like hello, for instance, well, that one is not. Right, so we can see that it seems to generally work pretty well for our examples here. Now let's finish analyzing this. So I said that this generally is going to be ON. This one right here in the worst case would be ON, right? We have to iterate the whole list of, or the whole array string once again, right? to iterate through the whole string in order to get our actual answer. So, that could be on in this case. However, there's also like a best case, right? The best case is that the first thing we compare doesn't match, which would be the fact that it's not a palindrome. So basically, in the best case, this looks to run in, constant time, right? So the best case looks to be constant time, but generally the worst case is on. And if we were to take a look at both of these together, we could say that it's, something like O of 2n operations, which really we generally will just like simplify down to O of n. It grows in linear time. It's a slightly slow linear time, but it's in linear time. So when I take a look at this, I'm thinking, well, okay, it seems to take a little bit of time to do, and the code is not very nice, right? It's fairly long. So I start to think to myself, is there a better way to approach this? And this is where we enter in the two-pointer approach. So the fact that we're iterating to get the reverse of the string is okay. But what we could be doing instead is we could be iterating forwards and backwards at the same time. What this looks like is if we had a string like race car, right? What I would do is I would start one of my pointers at the beginning of the array. So I'd have one index that points to the beginning of the array, and then I would have one that points to the end of the array. And what I would do is I would compare these two values together, and I would say, are they the same as each other? And if they are, then I would move this pointer over to the left one, and I would move this pointer over to the right one. So you see we just kind of keep moving them towards each other, and we keep comparing, and eventually they're going to meet each other in the middle. And if they meet each other in the middle and everything is matched, then the thing is a palindrome. This is a two-pointer approach. We have two different indexes that we're keeping track of, and we just move them towards each other until they meet each other in the middle. This approach is really ideal for a variety of different cases. One of the cases you're seeing here is if we have to do something to the forwards and reverse of a string, right? Another example would be basically any situation where we need to keep track of maybe two different pieces of information at one time going through the array, right? So this sort of approach looks like it may work a little bit better. Let's try it out and see what happens. I'm going to call this one is palindrome 2. So I'll call it is palindrome 2. It takes it a string as well, like our other example. And basically the way that this works is we say we're going to keep an end pointer, which is going to point to the end of our string. We're going to have a start pointer, which is going to point to 0, the beginning of our string. And then we have a, I'll keep it consistent here. I'll just call this palindrome, which is going to be true. And we're going to iterate exactly once. We're going to say, well, this is a palindrome and the start pointer is less than the end pointer. Like I said, when they meet each other in the middle, basically the start pointer will no longer be less than the end pointer. They'll either be equal to each other or it will be greater than it, which means that they've either passed each other or they've met each other in the middle. That's when we're going to stop iterating. And what we're going to say is we're going to say if the value at the start pointer, right, if this value is not an alpha num, then we're just going to increment that starting pointer by 1. We're going to move it forward, right? Otherwise, we're also going to check the end pointer. So we're going to say if the end pointer is not an alpha num, well, that we also just want to skip over. So we're just going to skip over those values. We don't care about them, right? And then finally, if they're both alphanumeric characters, well, then we're just going to go ahead and compare the value at the start pointer in lowercase, right? We're going to compare that to the value at the end pointer, and we want them to be the same as each other. And if they are the same as each other, then we continue our iteration. We move the start pointer forward one, which moves it to the right. We also move the end pointer basically to the left one, which is going to subtract 1 from it. Do you see how this almost mimics this loop here? It's basically the same process we took to reverse the loop, but we're just doing our comparisons at the same time as reversing the string, right? That's basically what's happening here. And this is actually really all we need. From here, all we do is we just return palindrome, right? If we've made it to the end of this iteration and palindrome is still true, well, then we are going to be good to go. Well, actually, sorry, there's one more detail here, right? So the else here would be palindrome equals false, right? Now we're good to go. So basically, if this piece didn't happen and both of them were alphanumeric, then, well, that must be false because the values didn't match each other, right? So that's the idea of this is palindrome 2. Let's give it a little test and see what happens. So with hello, I'm expecting that one to be false, which is what I get. If I do, say, race car, it's true, right? And if I do like mom, which is another palindrome, well, that's true. And yeah, that would be generally the idea of our palindromes, right? So let's go back to this. Let's take a look at this code here. So this code is cleaner, right? It takes way less space. It's way more efficient in terms of the actual amount of instructions that we need to run. And we take a look at the iteration. Now we actually reduce down the time complexity. In the worst case, this is still O of n. Technically, it only takes like half as many operations, right? Because on each iteration, we take care of 2 of the elements. So technically, it's n over 2, 1/2 of n. But since we don't really care about the constants, we could just say it's a linear generally. Where we see a really good improvement is that the best case here is still constant, right? But because there's no first iteration to reverse this string, we can actually get a best case that's fully constant. In this example here, the best case was always going to be O of n. The reason that it was going to be, or omega of n, right? And the reason why it's going to be always omega of n is because this iteration always happens no matter what. The best case only kicks in on the second loop, so we wouldn't be able to actually remove this first loop. But you can see here that this actually removes that first loop, so the best case becomes constant. This is more efficient generally in the best case than our first approach, right? So that's a nice improvement to this. So it's less code, it's got a better best case, it's technically got a better worst case because it takes less operations. And then one final thing that I'll point out to you is that we don't have to store a reversed string. This makes the space more efficient as well. We don't have to use any more space or memory. So this actually is done, as we would say, in place. It didn't require any additional memory for us to actually solve this problem. So that's generally going to be a nice improvement as well. So overall, this approach looks to be way better than our first approach. And this is really your first example of when algorithms come in really helpful, right? So you could see here that by us understanding a different kind of iteration, a different approach to algorithms, we can actually solve this problem faster, more efficiently than we did with our first approach to the problem. If you didn't know algorithms, you might have used this approach, and this would have been generally slower or a worse approach than this approach right here. So that shows you a bit more about the power of algorithms, why you might care about, actually using algorithms in your day-to-day. And generally, it gives you a new approach to iteration, which is the two-pointer approach, which we'll explore a bit more in the next video. So thanks so much for watching. I'll see you in the next one.